Then basically,
Sorry, I just recorded.
oh sorry, if let's say we have m elements of stabilizers, then because let's say we have G1, G2, and G3. So whatever group elements that we have inside this stabilizer group must come from these three elements. So it's either G1 to the power of 0 or 1, and then G2 to the power of 0 and 1, G3 to the power of 0 or 1. So, so these are the group elements for the stabilizer group for a particular stabilizer code. So because of this, you can really see that the number of elements inside the stabilizer group is 2 to the power of m. Okay. Over here, your Aj is either 0 or 1, and then m is the number of generators. So if we have some identity matrix, uh, and we sort of want equation 2 to be established, then your Aj has to be 0. So this condition is kind of similar to when we try to define the linear independence of vectors. So we just say that if we have this kind of equation, then if the basis vectors are linearly independent, then it has to be equal to 0 or something like that. So this is analogous to that idea. So then if we encoded a qubit, then we must also define what we call as the encoded logical operations. So as an example, if we use the repetition code, meaning we copy the 0 3 times, so this will be the encoded qubit 0, and this will be the encoded qubit 1. So the kind of operations that we can use to operate on 0 vector and the 1 vector is either XXX or ZII. So there are a few things that we need to take note of. The first thing is your encoder logical operations. They must be commuting with your stabilizers. Otherwise, your stabilizers will sort of like detect your logical operations. So in other words, your encoder logical operations, they must be the centralizer of stabilizer group. But they cannot come from stabilizer group, because if they come from the stabilizer group, basically it means the operations are trivial. And then third thing is, because if we want to define our Pauli X and Pauli Z operations, we already know that they anti-commutes. So that's why this is the third property. So these are the things that we need to take note when we try to define the encoder logical operations. So then there is a very nice equation that relates all three things together. So if we know the number of generators to be m, and we know how many physical qubits there are, then we can find out how many encoded qubits we have. So now we go back to the previous examples that we studied. So stabilizer states, such as the cluster states, because they fix the stabilizers, let's say G, they fix this particular state. So that's why you have 0 encoded qubit. So if you look at the 3 qubit repetition code, which is 000 and 111, so the stabilizer generators is ZZI and IZZ. So both of these generators, they preserve 000 and 000 and 111. So this has one encoded qubit.
So m minus n is 1. Sorry, n plus m is 1. Is it?
So you have 2 generators, and then your n is 3. So meaning that you only have one encoded qubit.
Good, okay.
Yes. So then you can also look at the stabilizer generators, ZZI, IZZ. with respect to the encoder operations that you perform. So you find that first, your Z, Z, I, Z, Z, they can't really generate your X hat and Z hat. No matter how you try, you cannot generate Z hat and X hat from these two generators. So the second thing is the generator, they commute with this thing, your Z hat and your X hat and Z hat. So basically, you can test it by yourself. Okay. So now we go into the idea of toric codes. So the idea of toric codes is very simple. Basically, you just define an L times L square lattice. So this is the simplest one that we will study. And you just define a periodic boundary conditions, meaning that this boundary and this boundary, they are periodic. So if you go up to here, you will appear here. If you go up to here, you will appear here again. Okay. So then the number, the circles that you see here, these are the qubits. And then this whole thing is called the placket. And then this cross is called the vertex. So this is the kind of like toric codes that we first study. Okay. So then, because now we don't actually need to write down the quantum state for toric codes, once we mention the stabilizer generators, then essentially we already have the system because of the stabilizer formalism. Okay. So there are two stabilizer generators. The first one is the placket generators. So over here is all Z. So this will be generators. So the other one will be the vertex generators. So this will be all X. So these are the two generators that we need to take note of. And then because from classical codes, we know that we can define the linear codes and then the dual codes. So over here is the same thing. So if the solid line here, so if this is called the primal lattice, then the dual code will be the dotted line over here. So this will be the dual code, dual lattice. So if you look at the primal lattice, so this will be the placket, right? So now if you look at the dual lattice, placket becomes a vertex. Whereas in the primal lattice, this is the vertex, but in the dual lattice, it becomes a placket. So there is this duality between the placket and vertex. So whenever we find one of the description is easier to describe than the other, we will refer to the corresponding lattice. Okay. So now, if this is a placket, so it's Z, 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 right? So if let's say I have another placket multiplied with the first one, so what will happen? So at this edge, because it's Z times Z, so meaning that this disappeared. So now your placket operator becomes something like this. Okay. So similarly for your vertex, if it is x, 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 if now I multiply another vertex operator, so this x over here, they sort of like, so is x, x equals to identity. So meaning that you just join together. Okay. So then we can start studying how many qubits that we encode in this kind of system by just multiplying all the placket together. And then eventually we will cover the whole lattice, right? And but the problem is, let's say over here you have L times L. So how many plackets operator? Basically you have L squared, right? And let's say P is your placket operators, and you multiply all your placket operators, and it actually becomes identity because you already cover your whole lattice in this case. So meaning that your placket operators, when you have L square of placket operators, they are actually not independent. So if you want to make them independent, then you just minus 1. So meaning that over here you have L minus 1 independent placket operators. So similarly for, sorry,
So this is to avoid the repeated multiplications on the inner of the qubits, right? Or the edges. Minus
no,
1.
not really. You just want a set of independent placket operators. It's just like you wouldn't define some basis vectors that are linearly dependent.
Oh, okay.
Yeah. In this case, you also don't want to have a set of placket operators that are dependent. So that's why if you multiply everything together, you get a set of dependent placket operators. So that's why you just minus 1 so that you get
Oh, the independent.
yeah, the independent ones. So meaning that for placket operators, you have L square minus 1 independent placket operators. So for the vertex operators, it's the same thing, but now instead of studying in the primal lattice, we can just study in the dual lattice, and then we get the same argument again, right? So meaning that in total, we have L square minus 1 placket operators, and then L square minus 1 vertex operators. So then we can proceed to calculate how many encoded qubits we have. So m equals to n minus k. So then your m is 2l squared. Wait, sorry. Your n is 2l squared. So you can see by here. So over here you have l qubits, and then you need to times l. And then over here you have another l qubits, and you need to times l. So meaning that you have 2l square qubits, physical qubits. And then your number of generators is 2 times L square minus 1. So if you perform this calculation, you get 2. Meaning that you have so many physical qubits, you can only encode 2 qubits inside here.
Oh, so the K encode qubits, right? Encoded
Yep.
qubits. Only
Yep.
2 for L square.
For all these 2L squared.
Yeah, 2L square, whatever L size is, right?
Yes.
Okay.
Okay.
Mhm.
So then the next thing is we want to define the encoder logical operations because we have 2 qubits. So we have x1, x2, and then z1, z2. Okay. So something to recall is first, your logical operations have to be commutative. with your bracket and vertex operators, but they cannot be the elements of your bracket operators or vertex operators, and they have to be anti-commute with each other because X and Z basically. So then you can try to study things that are of this nature, and you find that your Z1 and Z2, let's look at Z1 first. So if let's say you define this to be your encoded logical operations. So what will happen is for this bracket, you get -1. But for the rest, because they are not acting on the same qubit, you get +1 and so on. So how do you eliminate this -1 thing? So then what you can do is, oh sorry, not bracket because it's Z, so you have to look at the vertex operator. Sorry. So if let's say this is, we are trying to define what is Z1.
That's right.
Yeah, you should look at the vertex, not the bracket, sorry.
Okay.
So this vertex is all X, so that's why this vertex will detect your Z, so that's why it will get -1. Okay. So then, meaning that we need to eliminate this -1 thing.
Choong,
We
so in
need,
this case, -1 is your error, is it?
yeah, if you just define your Z1 operator as here,
Is that one? Okay.
so meaning that we need to put 2Z, right? Because if you have 2Z multiplied with x, 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 for example, so this will sort of like cancel off. So meaning that over here, now you detect +1. But over here and over here, you detect -1. So the only way for you to actually get +1 is doing this. You have a line of Z operators acting on this these qubits basically. So this is your Z1 operations. You can test. If let's say this is your vertex operator, you get +1, +1, +1, +1, and then +1, +1, and so on. And then other vertex operators, basically they won't detect this line. So you satisfied the first condition, they are commutative. And they are also not the elements from your stabilizer group, because no matter how you do it, you cannot actually generate this kind of elements by using your vertex operators. Okay, so the second thing, now we want to define what is x1. So following the similar arguments, if let's say you only have one qubit to be x, then this bracket operator will detect -1, while the rest detect +1. So in order for you to have +1 on this, then you need to put another x. But this one now will detect -1, so you need to put another x, and so on, until you form this line. So this is your x1 operators, and you find that it satisfies the first two conditions. So now the last one, they must anti-commute with each other. So this is your x1. If you draw a z1 over here, so this is z1, you find that the only place that they meet is here. So that's why you have x times z at this particular point, which will give you -1 or something like, I think something like this. So that's why all three conditions satisfied with this z1 and x1. For z2 and x2, you define on your world lattice. So you just apply the similar arguments, and you will get the z2 to be this, whereas your x2 will be just this. So then you can think about this, and you find that one of the circle will be your x, another one will be your z. And what is your bracket and vertex operator in this case? Is a circle on a torus. So this is where the uh, topological idea comes in, because these two circles, the x and the z, no matter how you deform it, you won't be able to string it to a point. Whereas your bracket and your vertex operators, if you deform it, they can actually string to a point. So then we look at how can we detect errors. So if let's say this is a vertex operator, this is a vertex operator, and this is the error. So only these two vertex operators will get -1. The rest of the vertex operators, you will get +1. If let's say now you have a string of a string of errors, z errors, so then this vertex will detect +1, whereas the rest will detect -1 and -1. So if you have a string of z errors, so this will detect plus, this will also detect plus, and then this will detect plus, this will detect plus. So you find that along the path, all your vertex operators will not detect the errors. Only the endpoints that will detect the errors to be -1. So that's the idea of how these toric codes actually detect the errors. So for the placket errors, you just do the same thing on your dual lattice. You can argue with the same argument. So in terms of fixing the errors, so how we can fix it? So usually if let's say this is the errors, and these are the vertex operators that we detected to be -1. So in this case, you can either applying back to the same error, which is E, or you can also go to another path, go to another path. So why does this work? Because if you consider about this, so this is your original error. And this is the path that you want to take to correct this error. And you find that this holding sum up is actually elements in your stabilizer group. Because this is just all the plackets summing up together. So that's why in this case, you have some freedoms to decide how do you want to fix your errors in this case. But we need to be slightly careful, because if this is your error, you can involve your X and your Z encoded logical operations in such a way that you can do this, or you can do this, or you can do something like this. So they are all equivalent in the sense that you fix the error, but you fix the wrong errors. Meaning that after you perform, let's say if you have this kind of error, but you try to fix your error by using this how should I call it? You try to fix your error using this path, it actually gives you the wrong answer. So because there is this inequivalent path that you already took. So that's why there's a process called the decoding process, meaning that you need to decide which path that you want to take to get back to the correct answer. So this is my last slide. The next one we will talk more about that decoding process.
So Choong, if in this case your last two slides, so you have how one can detect errors and how one can fix the errors.
For error detection is actually here. So meaning that so the point here that I want to stress is that you only detect the error at the end point. So along the path you can't really detect the errors. And then if you want to fix it, you either apply back to the same error, or you can apply a different path in such a way that when your error mixing with the other path that you choose, they actually become the stabilizer elements again.
So in terms of errors, it's either we are using the vertex or placket, right? Or combinations of. Is there any?
You can have X error, you can have Z errors. So in this case, I'm talking about the Z error.
Z
So
errors?
I look at the
Only
vertex.
vertex. Okay, okay.
Yeah. So if you consider the X errors, then you can look at your placket operators
Okay.
in lattice. It's the same thing.
Okay, okay, okay.
Yeah.
Right. So for this case, they always choose like five points, five vertex, just for the sake of examples, is it?
Yeah.
Yeah, of course you can go more. Like what? Well, we
You
only
can
have
go more
two.
actually.
Yeah, yeah. Okay.
But just for example, you can
Is it easy to read the? Is it the one that Hazazi shares? Is it? No.
for you mean the
Yours,
background.
your. Can you share the link, Chong, in the group?
I need to disconnect. So
Okay, never mind. Never mind. Later. Okay, that's from me.
it's actually here I have the notes here somewhere. Where is that? This one. So I just sort of like simplify a lot of things here. So you can have errors that looks like this, like a mess. Like you have this error here, and then this error here, this error here. So these highlighted vertex operators, they are the ones that can detect these kind of errors in this case. And the appearance of all these errors and how to fix it, it actually is related to quasi-particles. That's why I want to save it for the next one. And then the idea of, just now I mentioned that the X encoded operations and the Z encoded operations, they are basically the two circles from your torus. You need to look at homology. So there's actually a lot.
Homology.
Yeah.
Homology. Okay. I have
Welcome.
I have questions for you, Chong. I think from the message you may want
All
to
right.
read.
Should I stop sharing? I don't really understand relationship between the square lattice and the torus. Okay. So basically, how would you form a torus? So basically, if you have a piece of paper, you fold it and at one side, and then you fold it at the other side again, right? So this is how you form the torus. So in the square lattice case, it's the same thing. So you identify your periodic boundary conditions between, let's say, the left and right. So meaning that you are gluing the left and right together, and then the top and the bottom of the lattice, you glue them up together. So these two periodic conditions will give you the torus. Is there anything else? I don't think it's S1 times S1. Is it? Yeah, I think it's S1 times S1. Let me check first. Yeah, it's a yeah. I think it is related to that idea. So, anything else?
None from me.
Okay. So, want some informative